Welcome at Aldec's virtual booth. Thank you for taking your time to meet with us on DAC this year. My name is Krzysztof Szczur and I'm Hardware Verification Products Manager at Aldec. In this presentation, I'd like to share some ideas about in-circuit emulation. Let's first define what's in-circuit emulation, or in short ICE, because this term comes from the ancient times of electronics and it used to have a different meaning. So the heart of ICE is the emulation board, in our case main FPGA board, that's used to emulate the design under test. The DUT can be anything from an IP core, a subsystem, or a complex system on chip. Today's multi-FPGA boards are large enough to also accommodate synthesizable test bench components that generate additional stimuli for the DUT or convert test data received from host workstation to DUT stimuli. So our DUT is emulated in FPGA, which means that the FPGA is not the target chip technology for our design under test. Every design has several external interfaces that are mapped to the chip I/O that serve as a communication channel with external world. That's with external devices. An inherent property of in-circuit emulation is ability to connect with these external devices that make natural operational environment for our design under test. So let's look at the FPGA devices and so on the main FPGA boards. They provide a large number of external I/Os, making them convenient for expansion. So external peripheral daughter cards are used to deliver external device controllers. There is, however, one challenge in such an environment. Since the emulated DUT clocks have lower frequency than designed for the target chip, and the peripheral devices usually work at target speeds, it's required to connect additional buffering modules between the DUT and peripheral, and these additional blocks are called speed adapters. FPGA Fabric is also the good place to put such speed adapters. There is one more component in this environment, the host workstation, which greatly facilitates test management and implementing non-synthesizable test bench application. This test bench application orchestrates the entire emulation process. The same host workstation can be also used to control software and hardware debugging. As it was already mentioned, connecting external device with emulated design requires using a speed adapter block. I think that analyzing the PCI Express speed adapter application would be interesting for many because a growing number of application-specific SoC designs adopt the PCIe interface as a common interconnect with other devices that are readily available on the market. The PCIe devices use one or more high-speed serial I/O lines. Depending on the PCIe bus generation, the lines run at 2.5 GHz for Gen 1, 5 gigs for Gen 2, and 8 gigs for Gen 3. This is the lowest physical layer, and its gigahertz transfer rate clock is derived from a reference clock that may be, for example, 100 MHz. Both transmitting and receiving ends need the same reference clock. Any local buffers within each device are also clocked from the same reference clock source. Now let's look at the emulation side. A typical clock rate of design emulated in multi-FPGA board is around 10 MHz. Additionally, emulation clock may be controlled by the emulator engine or from hardware debugger software. The emulation platform should provide, for example, clock stepping mode for debugging purposes. So it becomes clear that the emulation clock cannot be used as a reference clock for the PCIe device. For this reason, we need to use a speed adapter module that on one side connects with the emulated design and synchronizes to the emulation clock, but on the other side it connects to the reference clock and to the high-speed serial I/O lines of the PCIe device. In case of advanced devices like PCI Express, implementing complex protocols, the speed adapter is not as simple as asynchronous FIFO. It needs to contain several protocol layers and at some point provide appropriate clock domain crossing circuit. In general, designing a speed adapter module for PCI Express is not a trivial task, especially if done from scratch. So let's check what it takes to design a PCI Express speed adapter appropriate for FPGA-based emulation environment. For this purpose, we'll use a system-on-chip design as shown in the block diagram. It's based on Xilinx MicroBlaze CPU, but any other processor like RISC-V or ARM cores can be used as well. So we selected Xilinx MicroBlaze because it takes very short. It takes half a day to put together such an SoC design with the CPU, SRAM, timer, interrupt controller, DMA block, and so on. All SoC main blocks are interconnected through AMBA-AXI interconnect. External peripherals include DDR4 memory, UART port, SPI flash memory, and PCI Express device. So we'll go through the design process of the PCIe speed adapter, but the remaining peripherals also require speed adapters. Note that the principles presented for the PCIe are applicable for the remaining peripherals. The PCI Express external device will be connected with the Network Interface Card. We would like to connect the SoC with local area network and expose it to the real Ethernet packets in the LAN. So this is how the actual design block diagram looks like. We chose MicroBlaze for the simplicity of the design. With MicroBlaze, entire design process could be done using Xilinx block diagram editor and ready-to-use IP cores from the library. The CPU, subsystem and peripherals groups are indicated with dashed lines, and note that they are interconnected through a customized AXI interconnect. For this system on chip, we selected several components and peripherals, and these are the components which enable building a Linux image to facilitate the software part of the SoC. The Linux kernel and available drivers can handle all the peripheral devices. The PCI Express device in our design is a root complex. That means our SoC can talk to other PCI Express endpoint devices, and the network interface card is one of the examples. The embedded Linux kernel can recognize the PCIe root complex controller, and further down the link it can enumerate and configure devices connected to the PCI Express bus. The CPU subsystem and AXI interconnect will run on the emulation clock domain, and peripheral controllers section should work as speed adapters, providing proper clock domain crossing from emulation to device clocks. Designing a PCIe speed adapter from the ground up would be a complex and time-consuming task, requiring a level of effort comparable to developing a complete device controller. But we have access to reusable components, like, for example, ready-to-use IP cores for PCIe bundled with Xilinx Vivado Design Suite. The AXI bridge for PCI Express will be appropriate for this task. It can be configured as PCIe root complex and provides all required protocol layers and also physical layer. The MGT lines are high-speed serial I/O. For the connection with the SoC, it provides 3 AMBA-AXI ports, M-AXI and S-AXI for data transfers, and another AXI slave for control commands. Let's also look into the clocking scheme. This IP core has input for a reference clock, which drives controller internals, and AXI clock output is derived from the ref clock. The AXI clock is needed to synchronize all AXI ports of this IP. So, how do we connect this IP with the rest of the design, which is in the emulation clock domain? The next block diagram shows what needs to be done to turn the AXI bridge IP into the PCIe speed adapter. We need 3 AXI clock converters connected to each AXI port of this bridge IP. AXI clock converter IP is also available in Xilinx Vivado IP library, and this module provides 2 ports. One AXI slave and one AXI master. Clock conversion means that the 2 AXI ports provide connection for the 2 corresponding input clocks, and so they can safely work on clocks with different ratios. And that's the demanded property of speed adapter. Please note that one clock line of AXI clock converter is driven from the AXI clock output of PCIe bridge IP, the red one, and the other one will be driven from the emulation clock, the green one on the diagram. We also have one more custom-made synchronizer for the interrupt line that's been written in VHDL. It's needed because the interrupt line is also fed back to the SoC subsystem, which runs in emulation clock domain. After I finished the design, there was the time for running it in hardware. For emulation, I have used Aldec HES US440 board that features Xilinx UltraScale US440 FPGA. Next to it is FMC PCIe extension daughter card, which allows connecting a standard off-the-shelf PCI Express cards, and it connects with the HES mainboard using a non-proprietary FMC HPC connectors compliant with VITA 57.1 and 2010 standard. On top of that setup, I connected a network interface card, which in our case is a PCI Express device. So now let me bring back the design block diagram to explain the complete test environment. The emulated design connects through PCI Express speed adapter to the network interface card and then to the local area network. But every design provides several status registers, and often this kind of information is drawn to the I/O and connected to LEDs on the board. In emulation, however, there is a more flexible and powerful way to get status data. You can use a host workstation and a co-emulation channel, which in case of Aldec HES-DVM is a scheme link. So I created a simple GPIO transactor and used scheme link to connect it to the host workstation. where simple test bench pulls the status registers and displays them in the console. The embedded Linux booted in the MicroBlaze CPU has its standard output messages redirected to the UART port. That's why UART is connected to the same host workstation, and I can observe embedded Linux terminal. The host workstation is connected with the network, so I can close the testing loop with the PCIe channel. If you are interested in this subject and would like to receive more information, please register for the live demo where our engineer will show how this emulation setup works and answer your questions. Now, let me briefly introduce the HES-DVM hardware-assisted verification platform. Hardware-assisted verification is a significant improvement of traditional simulation-based verification environments. It allows to sign off the chip with higher confidence and significantly shortens the bring-up process when the first chip production samples arrive to the lab. Thus, it can and should be used at all stages of design verification. At the beginning, when RTL modules are created and simulated, the FPGA board can be connected with the simulator. In this configuration, complex and long simulations can be accelerated for the benefits of hardware design and verification teams. Moving to hybrid co-emulation allows for system-level verification of the entire system on chip. At this stage, the FPGA board can be connected either with the system-level test bench on the host workstation or with the virtual platform or even with external peripherals. Both hardware and software teams can benefit from hybrid co-emulation. Hardware verification team receives a very fast model for running system-level regression tests. Any system integration problems can be traced conveniently in the simulation-like environment because the same test bench is reused during co-emulation. Software team receives a complete and accurate SoC model to run their software and firmware components without compromising any functionality. At the end of the day, the bug needs to be fixed either in software or in hardware, and at the time of hybrid co-emulation there is still a chance to do it at both sides, as opposite to late bug detection after chip tape-out. Physical prototyping is the last pre-silicon verification stage. Again, the same FPGA board can be used to implement and run entire SoC hooked with external peripherals and devices. Prototype implementation is optimized for speed, and so it's capable of running a complete software stack, including operating system, device drivers, as well as the main device application. Hardware debugging usually isn't concerned at this stage, as the RTL code is stable and frozen. Software last-minute verification and validation is the main task, and the last one before the chip tape-out. With Aldec HES-DVM, you can reuse one FPGA board throughout all design verification stages, starting from simulation acceleration and closing the process with physical prototyping. Aldec HES-DVM platform consists of hardware, software, and reusable verification components. HES boards are state-of-the-art FPGA prototyping boards available in various form factors and in single or multiple FPGA configurations. Software components facilitate integration with users' verification environment. DVM is a design verification manager tool, and it's used to automate design setup for FPGA. The bundle of verification environment interfaces allows for a quick and robust integration with many different verification environments and tools like simulators or virtual platforms. Reusable verification components contain a library of commonly used transactors and monitors like AMBI-XI, USB, or PCI Express. And last but not least, Hardware Debugger provides comprehensive debugging features to improve productivity while debugging corner cases that are detected during the emulation. A rich portfolio of HES FPGA boards contains single, dual, and scalable multi-FPGA systems. Aldec HES boards are built with the largest Xilinx Virtex 7, UltraScale, and UltraScale Plus FPGAs. Single and dual FPGA boards are often used as desktop emulation for the block level verification or even for system level while in co-emulation with virtual platforms. And desktop emulation is cost effective, so it can be replicated and shared across the corporate network to provide convenient access to many hardware and software developers. Multi-FPGA boards that additionally can be scaled up through backplane are ideal for larger SoC designs, emulation, and prototyping. Apart from FPGA prototyping boards, we also provide many compatible daughter cards with peripherals dedicated for different applications like Internet of Things, communication, automotive, and the like. For more information about available boards and other specifications, please check Aldec website. You can also benefit from our experience in board design by ordering custom boards if needed for your project. DVM, Design Verification Manager software, is a tool for design setup automation. It will guide you starting at RTL sources compilation through synthesis, partitioning, and FPGA bit file implementation. DVM provides two distinctive design flows, one for emulation and the other for prototyping. In emulation mode, that also includes simulation acceleration, DVM integrates verification interface with your design and provides behavioral compiler to convert transactors, monitors, and similar test bench components to FPGA. Your RTL code is compiled and converted to netlist using Aldec's fast synthesis engine. Then the netlist can be partitioned automatically into multiple FPGAs in case of large designs that don't fit in a single FPGA. ASIC-style gated clocks are automatically converted to clock enablers, and the user can also map non-synthesizable memories to FPGA or external onboard DDR resources. In-Circuit-Emulation, which we discussed earlier, requires connection to free running clocks or external devices. DVM facilitates connection of such modules. Another important part of emulation is hardware debugging. During design setup, the DVM tool provides source code instrumentation to preserve all required design internal signals and integrates the design with debugging infrastructure or the memory debug ports. The incremental setup flow allows you to save the DVM project at any stage and reload it if required. That works even if you change design sources, so you don't need to recompile entire design, but only the changed modules. DVM also integrates with FPGA vendor tools to automate the last stage, which is FPGA implementation, that's place and route and bitstream generation. You can also capture TCL script and use it in future for further setup flow automation. FPGA prototyping has different requirements and objectives than emulation. That's why separate design setup flow is provided by DVM tool. The main checkpoints in the prototyping flow are synthesis, partitioning, connecting, and FPGA implementation. Basically same as in emulation, but to achieve higher clock rates than in emulation, the user gains much more control over the partitioning and interconnection process. Like in emulation, every step can be fully automated, but the user can step in and modify the results or provide constraints for automation algorithms. For example, you can integrate your design partitions with the I/O serialization modules called interchip connectors, ICC, or you can decide to provide your own implementation of the multiplexers. It's also worth to mention that DVM prototyping flow is available as a separate tool or bundle with emulation models. The reason for having DVM prototyping separately is that it also supports third-party boards. You can create a board description file in System Verilog and using board compiler import it to the DVM and then use all the DVM powerful partitioning features the same way as with Aldec HES boards. Going back to emulation, it's very important to have advanced hardware debugging capabilities to be able to trace corner case design problems that often show up at this stage of verification. HES-DVM provides such debugging capabilities that will make you feel comfortable even if you step on the mine. That's a hardware bug. Static and dynamic debug probes extend your visibility space significantly and give you a choice between at-speed debugging or extended visibility. The HVD technology assures even 100% visibility, and the internal signals can be selected at runtime. Triggers enable automatic start of capturing debug probes, and breakpoints allow to stop emulation clocks under certain conditions. Full clock control provides determinism and ability to run design in single-stepping mode. The signals captured from FPGA are saved to waveform file with RTL names accuracy, so you can debug your design in context of RTL code and design hierarchy. Finally, memory visibility tool enables memory data upload or download at any time during emulation, which is a great help when running a processor-based system on chips in emulation. There are different design verification strategies, objectives, and goals. They all influence the choice of tools and methodologies and the shape of verification environment. Hardware-assisted verification becomes more and more popular recently, and we should be able to integrate it seamlessly with any tools and test benches. Interfaces are used to integrate hardware platform with the tools in the verification environment. Aldec provides high quality and large capacity FPGA prototyping boards that can be used for simulation acceleration, emulation, and prototyping, so capital expenses can be reduced by using a common hardware platform. So simulation acceleration interface contains support for Aldec and third-party simulators. There is a choice of signal level and transaction level approach depending on the test bench and design and use methodology. Emulation and hybrid co-emulation are supported by transaction level interface, which is compliant to Axelera SCIMI standard. Additionally, Aldec provides System C and TLM wrappers to facilitate connection with popular virtual platforms. In-circuit emulation that often requires connection with external devices running at higher clock rates is supported by the speed adapter dedicated features and multiple clock domain support. Finally, there is also a special interface in prototyping mode called HES-Proto-AXI. It provides speed-optimized host bridge and AMBA-AXI interconnection. It supports fast DMA and burst transfers, assuring high throughput data acquisition in prototyping test bench. The user can choose between C++ or Python API to develop test bench application that runs on the host workstation. So all the mentioned interfaces make a robust foundation in creating custom transactors and tailoring any kind of design under test with its test environment. There are, however, numerous standard interfaces like AMBA-AXI, PCI Express, USB, JTAG, UART, and the like. To reduce the test bench development cycle, you can choose one of the ready-to-use transactors and speed adapters from Aldec portfolio. We can also develop a custom transactor upon request. So let me summarize. Aldec is a one-stop vendor for FPGA-based hardware-assisted verification, and HES-DVM is a common platform for simulation acceleration, emulation, and prototyping. That concludes this video and my presentation. I hope that you enjoyed and that's been helpful for you. Thank you for attending.